Organized for inviting me to speak at this great workshop. So today I'm going to tell you about a paper that came out at the beginning of this year with Jeff Pennington and a fantastic graduate student at UC Berkeley, Gwanda Lin. So I think the introduction was mostly covered by Matt this morning, so I'll be very brief on the introduction. So I think in the last 20 years, we've learned there's a very deep connection between information theoretic concepts in CFT and geometric concepts in ADS. And the formula that really typifies this relationship is this HRRT formula, which says that if you want to compute entanglement entropy in a state capital psi in the CFT on some subregion B, then that entanglement entropy is equal to extremizing the area over all surfaces gamma, which are codimension 2, anchored on the boundary of this boundary subregion B. Okay, and the original formula only holds at leading order in large N, where n squared goes like 1 over Newton's constant, and in the infinite 't Hooft coupling limit, so always with no stringy effects. Okay. Now there's a proposal for what the quantum correction to this formula is, which Matt touched on this morning, which is that now instead of extremizing area and minimizing, you should extremize this generalized entropy, which is the sum of the area and this bulk entanglement term, which is the entanglement for fields living in this homology region sigma B. Okay. And to first subleading order in 1 over n, this was proven via the path integral by Faulkner, Lukowitz, and Nadasena, and then conjectured to hold at all orders by Engelhardt and Wall. Okay. And here I've said that they ignored the gravitons. What I really mean by this is that people said vague words about the graviton. And the goal for today's talk is going to be to say precise things about the gravitons. Okay. So why should we care about this formula? Well, I think this formula is very interesting, and in particular, in 2019, we saw that it could give a unitary page curve for black holes in ADS coupled to a bath. So I think that gave us evidence that maybe this quantum extremal surface formula is actually very interesting. Okay, and this page curve can be understood as some instanton effects in the gravitational path integral. There are these things called replica wormholes, which are some new non-trivial saddle that make the page curve come back down. But there's a lot more to a quantum theory than just instantons. We should be able to understand perturbations around a given saddle, and somehow we did the more complicated thing before we did the simpler thing. Like somehow the simpler thing is you have a saddle and then you look at perturbations around that saddle, and then maybe later you go look at some non-trivial saddles, and somehow we did it backwards. Like we found these very interesting non-trivial saddles even though we didn't know how to do perturbation theory around a given saddle. And the goal for today will be to try to explain how to include these gravitational perturbations in this formula. So for simple settings, we'll see today that in fact, these gravitational perturbations can dominate over the ordinary matter perturbations. And by dominate, I mean larger in a 1 over G Newton expansion. Okay, and why are gravitons hard? Why did people struggle for so long and only say vague words about them? Well, it's because you can't just really treat them as a massless spin 2 field. They interact with the area term in a non-trivial way because the graviton is really part of the metric. The area depends on the metric. And so the graviton has some non-trivial interplay with the area term, and you need to figure out how to deal with this area term. Okay. There's other complications with gravitons, which I'll get to, but I think this is a really fundamental one that we'll try to address in this talk. Okay, so what's the goal? The goal is to find a prescription for the generalized entropy of gravitons, and we're going to require that it satisfies 3 requirements. First, it needs to be gauge invariant with respect to perturbative diffs. The second is that we wanted to take a form of area plus bulk entanglement. Now, maybe this isn't a requirement, but it's certainly desirable. And the third requirement is that it agrees with the CFT entanglement entropy. So whatever we do in the bulk, we should be able to match to an independent CFT calculation. Okay, so these are going to be our 3 requirements for today. So what are the difficulties? Well, one is which entangling surface do you even consider, right? Yeah? Yes. Yes.
Does it mean that just the contribution from gravitons should be, you should be able to split into an area piece and a bulk piece?
Yes.
Okay, great, thanks.
So actually, I should comment that when we were working on this project, we found many formulas that satisfy 2 out of these 3 things. So you can actually write formulas that don't satisfy the second one. And the goal was really to get all 3 right, and that was the hard part. So yeah, this second part is actually more non-trivial than you might think. Okay. So yeah, so you need to figure out what entangling surface are you even considering, because now the geometry fluctuates. You have quantum fluctuations of the geometry, which are described by the gravitons. Okay, and you need to figure out what the area operator is on this graviton Hilbert space. I said that now the graviton appears in the area, so you can already predict that the area is going to be an operator. What is this operator? And how do you make it gauge invariant? And how do you make the whole generalized entropy gauge invariant? Okay. And then there's this old problem of how to define entanglement entropy for gravitons. So there's this old problem in gauge theories that the Hilbert space doesn't factorize due to gauge constraints that relate your region to its complement. And I actually won't have a whole lot to say today on this problem. It won't actually appear in our analysis very much, and you'll see why. But it's an old problem that people have struggled with. So usually what would we do if we wanted to understand how to derive a QES formula? Usually we would use the path integral. So Lukowitz and Maldacena taught us how to do the replica trick in gravity, and then it was generalized to one loop by these authors. But there's a problem when you try to do this for gravitons, which is that at the end of the day, you need to go away from integer n, integer number replicas, and at some point, you need the density matrix on a spacetime with a conical singularity, which is off shell. And it's very hard to figure out how to actually do this Lukowitz-Maldacena trick, or rather the quantum generalization by these authors when you have gravitons. And this is something we're working on, but I think it's still an unsolved problem. So instead, I'm going to do something else. I'm just going to do a direct Hilbert space calculation for the generalized entropy of the gravitons. Yeah, Matt?
I mean, it's not off shell in the original space time. It's only actually the overflow that is off shell. So why didn't it work in the original space shell?
Yeah, so you could try to define the gravitons in the smooth parent space, and define the gravitons there, absolutely. But then you'd figure out how to go away from integer n to actually take a derivative with respect to n to get entropy. So I think the Renyi entropies are fine, but to actually get the von Neumann entropy from that formula is, I think, a much more non-trivial thing.
I see, okay.
So today we're going to do a direct Hilbert space calculation of this generalized entropy, and we're going to match the CFT side to our prescription on the bulk side. Was there a question? Yeah.
Yeah, so sorry to come back to this off-shell thing,
Yes.
but what you mean by off-shell is that it's not a vacuum solution? Or
Yes, exactly. If you just do vacuum Einstein equations, it won't satisfy that because there'll be a Ricci.
there is this brain, or there is this conical singularity. Okay.
Yes, exactly.
But you can write equations of motion for that with this brain, and that will be a solution to that problem. But
Yes.
what you're saying is that it's not a vacuum solution.
Yes.
Very good, thanks.
Yes.
Maybe
Okay.
can
Yeah.
I do a comment also? So, I mean, for gravitons, thought just as a free quantum field theory, no,
Yes.
without back reaction,
Yes.
you don't really have that problem. I mean, the problem of factorization happens for also for scalar fields. I mean, it's just a problem of quantum field theory, and you can define it perfectly with the mutual information. Or, I mean,
Yes.
if so, I mean, there's no real problem for entanglement entropy for gravitons more than any other theory.
Well, I would say that the gauge you still have to figure out how to satisfy the gauge constraints at the
No,
entanglement.
you can do it just focusing on the gauge invariant variables, like for the Maxwell field. You can focus on the electric and magnetic fields. Here you can build analog of the electric and magnetic field with the Riemann tensor, and you can define. Well, we can discuss later.
Yeah,
but
let's
it is done in the literature.
Okay. Okay, good. So here's the outline for the talk. I don't know if I'll be able to get to all of this in the time, but that's okay. So at the beginning, I'll describe our prescription for how to deal with the generalized entropy for gravitons. Then I'll do some phase-space analysis of our formula. Then I'll tell you this explicit example where we can check both sides of the formula and make everything match exactly. And then I'll end with some conjecture and open questions at the end. Okay. So what is the prescription? Let me first tell you how you would do things for ordinary matter fields. So for ordinary matter fields, to compute this generalized entropy, say at first subleading order, you would consider a QFT on some asymptotically ADS spacetime in some state little psi. And then you would expand the metric around some background. So capital G is some asymptotically ADS background. And then you have some perturbation on top of that, which is order G Newton, which is your backreacted metric. And to solve for the backreacted metric, you solve Einstein's equation sourced by the matter in the state psi. Okay. And then with this, you then compute the entanglement entropy across the classical extremal surface, and you sum the two. Okay. So you get at first subleading order, the CFT entanglement entropy is equal to the area of this back-reacted metric for the classical extremal surface, which I'm calling gamma 0, plus the entanglement entropy of fields across the classical extremal surface. So sigma 0 here is the classical homology region. And there's an important point, which is there's no correction from the change in the surface, because it turns out to be a higher order effect in G Newton. And this formula at this first subleading order for ordinary matter fields has lots and lots of checks in various dimensions for various types of matter. I think this formula is very well established at this point. Okay, so now let's talk about gravitons and what's different. So now we're going to consider a metric, which is some background asymptotically ADS metric, plus our graviton, plus a back-reacted piece. Okay, so kappa here is proportional to the square root of G Newton. And this is the right coupling for the graviton in order to have a canonically normalized kinetic term for the graviton. Okay. So here's the action. It's not very pretty, but this is the action for the gravitons at quadratic order, just by expanding Einstein-Hilbert around this background metric G, which satisfies the background Einstein's equations. Okay. So now we need to talk about diffeomorphisms, which is a subtle issue when you're talking about perturbative gravity. So let's be clear what we mean. So there are background diffeomorphisms, which I'm calling here epsilon 0, which are proportional to kappa to the 0. And those change the background metric in the usual way, and they change the graviton in kind of a funny way. Okay? So these are the background coordinates, which we're going to fix. So we're going to fix some background coordinates. And then we'll have our perturbative diffeomorphisms. These are proportional to kappa. And these don't change the background metric, but they change the graviton in the usual way. And there's some effect on the back-reacted metric G2, but that's not important for our purposes. So these are the ones we actually care about, these perturbative diffs. The background diffs we just fix. Okay. Good. So let me make the first observation of our paper, which is that the area has to be an operator. So let's just go to first order, and let's focus on the perturbative regime, where the bulk entanglement is order 1. So there's no islands or evaporating black holes in this story yet. And let's study the generalized entropy up to and including these order 1 effects. So here's the classical area. I've expanded the metric little g in the expansion in kappa that I had on the last slide. And I'm expanding the surface here, gamma, around the classical extremal surface, gamma 0. Okay? So the leading order in kappa, this is the only term you have when you expand this classical area functional. And is there a way to treat the area term classically? So that's the first question you might want to ask. And the answer is no. This would not be consistent with the CFT. In particular, for the CFT entanglement at this order, so this will contribute at order 1 over kappa in the bulk to the generalized entropy. And if you consider a single particle state like this, a single graviton state, then the trace of this state needs to be 0, but for a superposition of the vacuum and a single graviton state, it needs to be non-zero. So this is what you find for the dual states in the CFT, and this will be true if the area is an operator by promoting H in this formula to the graviton operator. So if you do that, then these are all perfectly consistent, and in fact you can exactly compute this in the bulk and match it to this non-zero answer you get in the CFT. So this is the argument that the area has to be an operator, because it needs to vanish for individual states like this, but not vanish for the superposition. Okay. Good. The second observation is that classical perturbations are not enough. So how do you see this? So here, let's now go to order kappa squared. So here I've expanded the classical area functional to order kappa squared. So there's a term that depends on, that's quadratic in the graviton. A term that's linear in H, linear in gamma 1, but quadratic in their product. So gamma 1 here is a perturbation of around the classical extremal surface. There's a term that's quadratic in this perturbation of the surface. And then there's a term that's linear in the back-reacted metric G2. These are all the terms that you could write down at this order. And classically, this will only be gauge invariant if gamma 1 extremizes this whole area functional term. Okay. And so what you could do is you could naively just try to promote the area to an operator like we did on the last slide by promoting H to the graviton operator, H hat. And then you would see that for these single particle states, this area would just vanish, okay? And if you just treated just H as an operator, and in fact, this would not be a gauge invariant statement. The thing that's gauge invariant is you should have all of these terms to be non-vanishing, okay? So the correct thing to do there's two options. One is you can either promote the surface fluctuation to an operator, which is the one that I'll pursue for most of this talk, or you can gauge fix the surface classically and extremize over gauge equivalent states. The second one is more complicated, and I'll discuss it only at the very end of the talk. So for now, we're just going to focus on this first one, and we're going to promote gamma 1 to an operator. That will make this area operator a gauge invariant. Okay. So you'll see later how we make gamma an operator. It'll be a well-defined operator that will make the area a gauge invariant. Okay, so the third observation is that there's this infinite set of interactions that I didn't write down. So I told you the quadratic term for the graviton, but there's of course an infinite set of higher order interactions when you expand Einstein-Hilbert order by order in kappa. And so we have to figure out if these could contribute. So in particular, this term, I told you for the single particle state at order 1 over kappa, the generalized entropy vanished. So that's at leading order, that's at order 1 over kappa, but it can receive higher order corrections from, say, a cubic interaction in the action. And you might worry that these terms are important. But what we actually proved in our paper is that by backreacting, so you solve the backreacted Einstein's equations for the quadratic Einstein tensor of H to solve for the backreacted G2. If you do this, then the free theory for the gravitons plus the backreacted metric is actually the same as including the cubic interaction. So the philosophy is that you can just backreact at this order and treat the graviton as free. Okay, so the backreaction is taking into account these interactions for you, even at the quantum level. Yeah.
If you include those corrections, you shouldn't change as well this issue with the diffeomorphism invariance, that you only treat quadratically as well.
Yeah, it'll still be diffeomorphism at the next order.
Yes.
Yeah.
And this would hold?
This would hold, yes. So this formula would still hold. We haven't proved it to all orders, but at the cubic order, yes. Okay, good. So to order 1, which is the regime that I'm studying for now, for the generalized entropy, you can just do this. Backreact and treat the graviton as free. And this turns out to be the correct quantum prescription. Okay. So the last thing I want to talk about is the bulk entanglement entropy. So we're going to look at vacuum subtracted von Neumann entropy. This will be the simplest thing to consider. And it will be UV finite for the free theory. Okay. Morolf and Wall showed that for interacting theories, you can get state-dependent divergences. But for the free theories we'll be considering, this will be a UV finite quantity. Okay. And now here's the von Neumann entropy. I've written it as the trace of the density matrix times this modular Hamiltonian, which is minus log of the density matrix. And here's the vacuum subtracted entropy. So here, I've really considered the difference between any two states. So here I'm looking at the difference of the entropy between a state phi and a state psi. And I've done a trivial rewriting, which is you can always rewrite it as the difference of the modular Hamiltonian for psi in these two states minus the relative entropy. Okay? And this relative entropy can always be well defined in terms of gauge invariant operators. So this relative entropy is a well-defined quantity. It has no ambiguities in the continuum. On the other hand, this first term, this modular Hamiltonian term, is not a well-defined operator in the continuum. What is well-defined is the two-sided modular Hamiltonian, where you look at the difference between the modular Hamiltonian for the homology region minus the modular Hamiltonian for the complement. That's the well-defined operator. And so there's a question of what is the right definition for this k psi, for the graviton. And it has these ambiguities due to boundary terms. So you can always add a term on the boundary of the homology region, in particular on the entangling surface, that won't change this well-defined two-sided operator, but it will change this one-sided operator. So there's this ambiguity up to boundary terms, and you have to figure out how to fix these. And it turns out that there's a way to fix these by requiring that there's no boundary term in a special gauge. And I'll come back to this later in the talk. But it turns out that that choice of this modular Hamiltonian agrees with the CFT result. I should advertise that I have some work ongoing that I think can actually prove that this is the only modular Hamiltonian you can write down. But you can ask me about that after if you're interested. Okay. So now let me tell you our prescription. So let's quantize the graviton. So here I've expanded it in modes where I've labeled them by the quantum number q. Then the claim is that for any graviton perturbation around a state with a classical extremal surface, you can do the following. So you can find a linear map that constructs for you perturbed surfaces gamma 1 that are extremal. So this is a classical extremization problem Here K is the extrinsic curvature, and I labels the two normal directions to the surface. And here you can require that for gamma 1, the surface is still extremal. And that solves for you this gamma 1, okay, in terms of H. So H is some gravitational wave, some classical gravitational wave. You extremize with respect to that classical gravitational wave, and you get the perturbed surface, gamma 1. And now you can go ahead and construct a Hermitian extremal surface operator from this perturbed surface. So this is how it's defined. In exactly the same way as the graviton, but instead of the graviton wave functions, you now have these perturbed extremal surfaces, okay? And this defines for you an extremal surface operator. There's a different thing that you could have done, which is actually equivalent, which is write down an arbitrary operator like this, and then extremize the generalized entropy. And that will pick out the same gamma 1 Qs as this classical linear map that I've defined here. So they're equivalent. But once you do this, this actually gives you a gauge invariant area operator. Okay, so now here's the area operator. Gamma is now an operator. And you have a term at order 1 over kappa, which is linear in H. And then you have all these terms which are order kappa to the 0, plus the bulk entanglement entropy term. Okay, so this is the full entanglement entropy, generalized entropy for the gravitons. And then the claim of this talk is that the vacuum subtracted entanglement entropy in the CFT for a state capital psi is equal to the vacuum subtracted generalized entropy defined in this way. Okay, and we call this the fluctuating surface prescription. And we claim that it only holds to order kappa to the 0. I'll say at the end some comments about higher orders in G Newton, but for now, this is the claim. So why is there a delta here? Why did I not say S? The reason is that I don't know how to compute S. I don't know how to compute the entropy itself in the CFT. And it's also a divergent quantity, and there's many complications coming with the fact that it's divergent. And on the other hand, this formula, both sides are finite. I actually know how to compute both of them in the bulk and in the CFT, and so I can just go ahead and check if this complicated formula that we have here is actually correct or not. Yeah, Matt?
Defined in the CFT, is that because of the entangling surface? Or?
Well, it's not that it's not defined. There's some divergence. You have to put in some cutoff. But it's more that I just don't know how to compute it. So like the techniques that I'll show you later in the talk, in the example, I can explicitly compute some number that computes this thing. And I don't know how to do that for S itself.
But the issue is the entangling surface?
The issue is just how you can do the replica trick in higher dimensions. It's very complicated. So in dimensions greater than 2 in the CFT, I think it's very hard to do the replica trick. But actually for delta S, you can do it. Right? So how do you compute the entanglement entropy in higher dimensions? You have some higher dimensional twist surface operator, and you need to compute its correlation function. I think that's a very hard problem.
So again, it's the entangling surface. Yeah. Sorry to keep repeating my question.
Yeah. So if you want to think of that twist, that twist operator.
Okay, so you could just consider a situation where there's no entangling surface, right?
You mean take the entire boundary?
Yeah.
Yeah, I don't know how to extract just the graviton fluctuations from that formula. We should talk about this offline. I don't know how to extract.
I mean, you have the same. I just want to say that like the bulk and the boundary issues are just separate. So you can address all of your bulk issues with gravitons without addressing at all the fact that the QFT has issues on the entangling surface by just considering a situation where the surface.
Yeah, so you want to just take the full boundary.
Yeah, well, a connected component, something.
And consider, say, some
like a multi-boundary wormhole, and then.
I see. And then consider some stress tensor excited state and try to compute the entropy. Maybe you can do it.
I'm just saying that these are totally separate things. The boundary issue with the entangling surface and the bulk issue with the graviton fluctuations are just, I think they're totally unrelated things. So.
Yes, I agree that they're unrelated. It's just, I didn't know how to compute that CFT quantity. Maybe you know how to do it, but I know how to compute
you can do the replica trick, and then you don't have any twist operators. So you're in good shape.
So then you just have a bunch of stress tensors. Yeah, maybe that's not hard. It's just some correlation function of stress tensors.
We can talk about it later.
Okay. Okay, good. So let me, before I move on to the phase space analysis, I want to take a closer look at this order 1 over kappa phenomenon, because I actually find this very interesting. So from the bulk perspective, it was clear that you could get generalized entropy at this order. You just take some state such that the graviton has a non-zero expectation value, and the area is linear in the graviton, so then you'll get a non-trivial area term at order 1 over kappa. So we saw this for the superposition states. So you take a superposition of the vacuum in a single particle state, and you can get this kind of very large generalized entropy that's larger than you would get for ordinary matter. But from the CFT perspective, it's rather strange. So you have two states. Neither of them has large entropy difference above the vacuum, but somehow the superposition does. So I want to try to give some intuition for why this is true. So the next part is not going to be precise. It's just going to be some heuristic intuition for why this might be true. So let's think about the thermophile double state. And there, the energy expectation values and its fluctuations are large. So if I take the right Hamiltonian for the thermophile double, it has an n-squared expectation value. So I can subtract off that expectation value. So now this new operator delta H has a finite, in fact, 0 expectation value. However, the fluctuations will still be order n squared, and the 3-point function will be order n squared, and so on. Okay. So now if I look at the graviton state, which is roughly delta H over n, this is the right normalization to be dual to the graviton, then if you can look at the superposition, there'll be a cross term, which will be like the 2-point function of delta H with only one factor of 1 over n. This will give you some order n entropy. Okay, let me give you another perspective on this, which is you can think of it in a Gaussian way. So write the TFD like this. Alpha will be some Gaussian amplitude for the TFD. Here S is the microcanonical entropy. And then the TFD will just be this nice Gaussian centered at some E0, which is the average energy of the TFD state. And if you look at delta H, then alpha will just have some relative phase between positive and negative energies, but the average energy doesn't get shifted at all. On the other hand, the superposition state, which is this green curve, the average energy actually gets shifted by order n. So you can see there's constructive interference of positive energies, and the negative energies actually get destructively interfered. So this is some intuition for why the superposition can actually increase the energy and hence the entropy by an order n amount, or order 1 over kappa amount. Okay, so here are the basic takeaways. We found a prescription which is gauge invariant with respect to perturbative diffs. It takes the form of area plus bulk entanglement, and we'll see later in the talk that it agrees with the CFT entanglement entropy. We saw the area needs to be an operator. It's a well-defined operator, and it's gauge invariant on the graviton Hilbert space. And there's this large class of states which have parametrically larger entropy than any ordinary matter fields. Okay, so let me do some phase space analysis of this formula. Maybe actually I should skip this for sake of time. Let me just skip the phase space stuff and go to the example. Okay, good. So now let's do an explicit example to actually check this in a d-dimensional CFT. So here I have an arbitrary d-dimensional CFT on the cylinder, and all I require is that it satisfies the condition that CT, which is the coefficient, the 2-point function of the stress tensor, is much larger than delta gap, which is the conformal dimension of the lightest single trace operator with spin greater than 2, which is much greater than 1. So CT being large suppresses Planck scale physics, and delta gap being large suppresses string scale physics. Okay? And in general, CT you can think of as like n to some positive power. So in all known holographic theories, this is the dependence of CT with n. So these are the only assumptions that I'll need in order to do the CFT calculation. So these were shown by Heemskerk, Penedonis, Polchinski, and Selly to be necessary conditions for a holographic CFT to be dual to weakly coupled Einstein gravity. And now we're going to consider some excited primary state, which is the stress tensor acting on the vacuum at the bottom of the cylinder, with some polarization tensor which we'll fix later. And the subregion that we'll consider is a polar cap subregion B of some size theta naught on the t equals 0 slice of the cylinder. Okay? And now let's construct our reduced density matrix. So to do this, we'll use this Cassini-Huerta-Myers map, which maps the cylinder to hyperbolic space at finite temperature. And under this map, this subregion B gets mapped to all of hyperbolic space at time t equals 0. And the entangling surface gets mapped out to infinity. It's this blue curve. And these stress tensor insertions creating our state, which were at the bottom and the top of the cylinder, get mapped actually very close together on the thermal circle, and they're at the bottom of hyperbolic space. Now this turns out to be a key point, because as you take the small theta naught limit, these two stress tensors will actually become close, and you're in the OPE limit. This is what makes the computation tractable, is this Cassini-Huerta-Myers map that puts the two stress tensors very close. Okay. And now the other key fact about this map is that the reduced density matrix on this polar cap just gets mapped to the thermal density matrix on this hyperbolic space. Oops. And the excited state, again, takes a very simple form under this map. Okay, good. So now we can go ahead and compute the modular Hamiltonian to compute the entropy. So let's expand around the vacuum. So we can think of our stress tensor excited state as the vacuum plus some perturbation. And then the modular Hamiltonian, which is log of this density matrix, takes an integral form like this, which you can expand in an infinite sum around the vacuum density matrix. Okay? So you have the vacuum modular Hamiltonian plus an infinite set of corrections, delta k. And this delta k has a very nice form, which was derived by these authors in 2017. In particular, it has an explicit integral form like this. So you can think of this as modular flow of the perturbed density matrix by the hyperbolic Hamiltonian, integrated against some kernel, okay? And so for every correction, you have to do more and more of these integrals. And this kernel has some explicit form that looks like this. But the key point is that for small theta naught, delta rho is small. So order by order in theta naught, you don't have to do this full sum. You just go to whatever order in theta naught you care about, and higher terms in the sum will be suppressed at small theta naught. Okay. Good. So now we can go ahead and compute the von Neumann entropy. So here's the vacuum subtracted von Neumann entropy for our excited state. And you get the vacuum subtracted vacuum modular Hamiltonian. You can think of this as the first law of entanglement entropy plus some infinite set of corrections like this. Okay. So the infinite sum gives the relative entropy. That's what this infinite sum is. Now, because we're working in this very simple case where we just had some very symmetric region, the modular Hamiltonian for the vacuum is actually just some integral of the stress tensor. Okay? And that means that to compute this vacuum subtracted vacuum modular Hamiltonian, it's just a stress tensor 3-point function. And that's completely fixed by conformal symmetry and conservation up to 2 theory-dependent constants. On the other hand, this relative entropy will be, the nth term will be 2 endpoint functions of the stress tensor, which are again theory-dependent. Okay. So far we haven't used our assumption yet, so now let's use this assumption on our CFT to compute these quantities. So if you make these assumptions on the CFT, then in this beautiful paper by these authors, they showed that crossing symmetry completely fixes the stress tensor 3-point function to just be the Einstein-Hilbert 3-point vertex. Okay, so then you can go ahead and compute these integrals. You get some ugly answer, but the point is it's some non-trivial thing we need to match to the bulk. And similarly, you can compute the relative entropy. It's some integral of stress tensor 4-point functions, and you can use large N factorization to write it as a product of 2-point functions to get this simple result. Okay, so this is the complete answer now for the vacuum subtracted entanglement entropy in the CFT. I'm going to move on to the bulk calculation. Are there any questions about the CFT calculation? Yes, it does. I don't remember how it simplifies, but it is simpler. Because you don't even need these assumptions, because stress tensor correlators in 2D are just fixed by Virasoro. Okay. Good. So now let's talk about the ADS part of the calculation. So let's consider global ADS, which looks like this. And let's consider the full unconstrained phase space of the H and its conjugate momenta. And I'm going to choose a radial gauge, which turns out to be the simplest thing to do. So we're going to gauge fix, we're going to impose our constraints, and we're going to construct a reduced phase space, which comes equipped with some Dirac bracket, which then gets promoted to a commutator when we quantize. Good. So now let's quantize the theory. The graviton can be decomposed in terms of the SD-1. So ADS has this SD-1 part of the metric, and you can decompose the graviton in terms of scalar, vector, and tensor modes on the SD-1. And then they completely decouple, so the Hilbert space is just the tensor product of the three types of modes, and the mode expansion of the graviton is just a sum over the three types of modes. And then there's an extrapolate dictionary which relates this graviton to the stress tensor in the CFT, which we use to define our CFT state. And I'm going to focus on this lowest energy scalar mode. So take the lowest energy mode. This is no radial excitations, angular momentum equals 2, and no azimuthal angular momentum. This turns out to be the lowest energy mode, which is dual to the stress tensor state in the CFT for some particular choice of polarization. And it turns out you can actually analytically solve the wave functions for this mode. That's what will allow us to actually compute the generalized entropy. Okay, good. So now that once we have the wave functions, we can go ahead and just compute gamma 1 by extremizing the area with that wave function. It looks like this. So gamma 0, this orange curve is the classical extremal surface, and the magenta is the perturbed extremal surface. And you can also analytically solve for the back reaction of this mode on the metric to find the back reacted metric. And then you go ahead and compute the area. And again, you get some complicated result, but you can go ahead and compute it. And you can do it for any dimension. Here I wrote it for d equals 4, but you can do this calculation in any dimension. Okay, good. So that's the area contribution, and now we have to go compute the bulk entanglement. So here's our graviton wave function. I've plotted one of the terms in the wave function, one component. And so the point is that here we have some ADS-Rindler wedge, sigma b, and its complement, sigma b complement. Here's the classical extremal surface gamma 0, and we want to trace out the left wedge and compute the entanglement across gamma 0. Okay. So now we need to go ahead and quantize the graviton in Rindler. So here I've written Rindler coordinate, ADS-Rindler coordinates in a very nice form, where the classical extremal surface is at tau equals 0, rho equals 1, and this piece of the metric is hyperbolic space. And now we go ahead and do the same thing we did in global coordinates, but in a different gauge. Now it's very nice because our generalized entropy formula is gauge invariant. So it doesn't matter now that we're picking a different gauge in Rindler than we did in global. So here we're going to pick Rindler radial gauge. And again, you can decompose the graviton now on the hyperbolic part of Rindler metric and quantize. Okay, good. And so now to compute the entanglement, you have to relate these global and Rindler modes. So here's the global mode, and it's a sum over the Rindler modes with some Bogolyubov coefficients. And these Bogolyubov coefficients encode all of the information about the entanglement. So it turns out that this scalar global mode is only related to the scalar Rindler mode. So you can actually, the problem simplifies dramatically, and you can just compute those Bogolyubov coefficients. And you can compute them analytically at small theta naught in a gauge invariant way. So now you go ahead and you compute your excited state density matrix for the gravitons. So the thermophile double state for Rindler is the ADS graviton vacuum. So I've written it like this. And then the reduced density matrix is just the thermal density matrix for ADS-Rindler. And the modular Hamiltonian for the vacuum is just the Rindler Hamiltonian. You can use some nice relations of the Bogolyubov coefficients and the Rindler modes to rewrite everything in terms of operators on the right. And then it's simple to trace out the left. So you just get this very simple reduced density matrix for the graviton excited state in ADS-Rindler. And you can see that all the information is just encoded in these Bogolyubov coefficients. Okay. So now to compute the entanglement entropy, we're going to use the replica trick, but not the usual replica trick where you replicate the manifold n times. We actually have the density matrix explicitly. And so we're just going to directly compute n copies of this density matrix and take a trace over the Hilbert space. And then take a derivative with respect to n and set n to 1. So you can just do this explicitly. And again, at small theta naught, we can perturb around the vacuum density matrix. So the excited state is some small perturbation around the vacuum. And then at leading order in this delta rho expansion, you just get the first law of entanglement. So you get this vacuum subtracted vacuum modular Hamiltonian. It's some integral of the Bogolyubov coefficients, and you get some complicated answer. You can do the same thing to next order to now get the relative entropy in the bulk. And you get some simple quantity like this, which we call rho tilde of n, which you can explicitly analytically continue in n and set n equal to 1, and you get this quantity. And you can again write it in terms of Bogoliubov coefficients and compute the relative entropy. Okay, good. So you can put all this together, you can add it to the area contribution, and you get exact agreement with the CFT result. So I think this is a strong indication that we found the right formula for the generalized entropy for gravitons. We had to do some very complicated boundary calculation, some very complicated bulk calculation, and at the end of the day, everything matches, okay? And everything's gauge invariant. So I'm going to skip this stuff about edge modes as well because it didn't actually play a role. So we don't think that the edge modes actually contribute to these vacuum subtracted entropies, so that's why I think I should just skip that. Let me talk about something more interesting, which is an all orders prescription. So this is how we think that this might work if you were to try to go to all orders in G Newton. So far we've just analyzed 1 over square root G Newton and order 1. And it's not clear how to extend this fluctuating surface prescription to higher orders, and also how to include ordinary matter. These are both things that we thought a lot about, got very confused about, and decided that there might be a simpler way. So let me tell you what the simpler way looks like. So instead of doing the quantization here, where you first gauge fix the graviton and then quantize, you can do something else in gauge theory. You can do this refined quantization or group averaging method for perturbative gravity. So now states are not required to be gauge invariant, but there's an equivalence relation which says any two states are equivalent if they differ by a diff acting on any other state. Okay, this is a nice way to quantize gauge theories. And then you have an inner product that respects this gauge equivalence by integrating over the action of the gauge group. So here, U of G is the element of the Lie group acting on this state, and you integrate over all elements of the group. You can equivalently write this as just a product of delta functions of the diffs acting on the state. And then it's clear that this inner product respects this equivalence relation because the delta of pi's just kill this pi phi. Okay? So this defines a gauge invariant inner product. So then the prescription is the following. Okay? So you can define what we called quantum extremal gauge for the state psi by requiring that the following operator kill your state psi. So the operator is the commutator of any diff with the generalized entropy operator. Okay, so this defines a gauge for psi. In particular, it picks out a particular representative of a given equivalence class. Okay, and so you can think of this condition as like an extremize over states. So before we were extremizing over geometries, over fluctuating geometries to define this gamma 1 hat. And now we've completely removed gamma 1 hat. Everything is in terms of the classical extremal surface gamma 0, but now we extremize over states. Okay? Yeah.
Maybe a naive question. So that commutator in
Yes.
what Hilbert space is computed?
This commutator is in the perturbative graviton Hilbert space.
But you are talking about generalizing for non-perturbative. I mean, like for general diffeos, no?
Only perturbatively in G Newton, yeah, not non-perturbatively.
But if you take more orders in perturbations, I mean, you also need to change you cannot stay in linearized diffeos.
Yeah, so this PI will not be the diffs that I wrote at the beginning. You'll have corrections.
But I don't see then what is the Hilbert space in which you are computing that commutator. It seems that you are using some operator. I mean, it's supposed to be a more general thing. The commutator is supposed to be Hilbert space of.
Yes.
I don't see that everything is matching.
So you have the free Hilbert space, and then you can, in perturbation theory, you can write down interactions in acting on that free Hilbert space, right? Like just what you do in any interacting quantum field theory. So you define your Hilbert space in terms of the free theory, and then you define interactions on that Hilbert space. So you can still do canonical quantization even in interacting
if that's the
theory.
problem you want to solve for saying that you have a prescription to higher orders of the entanglement entropy for gravity.
Yes.
Because it's a different problem. You're considering just a problem that also is kind of ill-defined. I don't know if you can do that for the graviton because it has no stress tensor. So if you treat it just as a field theory, you cannot include interaction so easily. So, I mean, yeah, I don't know.
You can formally define this quantum field theory by expanding Einstein-Hilbert. I agree there's issues with non-renormalization and so on, but I think if you truncate at some order, you can just define, and you put in some cutoff, you can just define that quantum field theory. at some order. Let's say you want to go to order G Newton to the 5th, and you put in some UV cutoff, then you can
But what
define,
would be the gauge invariance that you are using at that order?
Yeah, there'll be corrections to the one that I wrote originally.
So yeah, so that's the point. Okay, we can discuss.
Okay. Okay, good. So this is the quantum extremal gauge condition. And then even though each of these two terms is UV divergent, it's expected that after renormalization of G Newton, this operator is actually a well-defined operator. So Matt touched on this a little bit in his talk, but it's expected that this is a well-defined operator. So then this is a well-defined commutator. But notice that this is not gauge invariant because we don't have gamma 1. So this commutator is really non-zero. Otherwise, this would just be a trivial condition. But it's not trivial because pi doesn't commute with this operator. And in principle, we don't expect it to commute with this operator either. Okay, so this is some non-trivial gauge fixing condition. And then the conjecture, which we have no evidence for, but agrees with the thing that I already told you, to the orders that I already told you, is the following. So instead of, you've already done this extremization over states. So now you just minimize over all states, which are gauge equivalent to this, this state, because this is only a partial gauge fixing. You minimize the gauge invariant inner product of the QES operator and minimize over all such state psi, a gauge equivalent to the state, psi tilde, gauge equivalent to the state psi. Okay. That was a conjecture of how things might work to all order. It seems to make sense, but we have no evidence for it. But it is equivalent to the original prescription that I told you. Okay, so now let me end with some open questions. So can we better understand this all orders prescription? We've been thinking about it a little bit, but it seems very hard to do anything concrete with that prescription. One question is, does such a quantum extremal gauge exist in every gauge equivalence class of states? That was something that we've had trouble proving. Is the generalized entropy of all such states even bounded below, so you can even do the minimization? And there's this question of how to derive things from the path integral. So this is something that Matt was asking me at the beginning of the talk. And it's a bit confusing about how to do the analytic continuation in N for the gravitons. You could try to work in the smooth parent space and compute one loop determinants on that geometry, but you need to write them in some way that's analytic in N. It's not clear how to do that. If you try to actually go to the quotient manifold, then you have problems with gravitons propagating on off-shell backgrounds. So Andreas and I wrote a paper last year proposing one way to deal with this off-shellness, but it'd be nice to have a more principled derivation. Okay, there's a more technical point, which is more for the experts in the audience, but there's a question of how you actually relate diffeomorphisms on the smooth replicated manifold to this quotient space, if you choose to try to use the quotient space. And how do you make sense of the area operator from this perspective? And I think the holy grail of all of this, which is what we're trying to go towards, is how do you actually understand the QES formula in terms of quantum gravity? So originally, it seemed like it was just some formula about QFT in curved spacetime. And then we had this page curve formula, which seemed to tell us that maybe it knows something more about quantum gravity than we originally thought. Maybe it knows something more about QFT in curved spacetime. And this is sort of the 0th order step that you would try to do to embed the QES formula in quantum gravity, which is just include gravitational perturbations. But I think to really do this, you need to understand how to embed this low energy effective field theory in string theory. So the question is, how do you embed the QES formula into perturbative string theory? And I think this is really the holy grail to understand if it's a quantum gravity formula or not. Okay, thank you.
So back to the 2D case.
Yes.
In the bulk, there's no on-shell gravitons.
Yes.
So what actually contributes? Is there a contribution, or?
You still have boundary gravitons.
Uh-huh.
And I would expect it's a little bit trivial. I would expect that what you're just matching is stress tensor correlators in the 2D CFT to just boundary gravitons in the bulk. And I would expect that it's not that interesting in that case.
So the off-shell gravitons do not contribute?
They don't seem to contribute in this formula. I mean, if you're just doing canonical quantization, you don't seem to see the off-shell gravitons of even in 3D.
I see. Can I ask you a second question? I don't really understand your holy grail. I mean, what is it that, I mean,
well,
what is it that we would learn? Is it that we're having UV problems in the bulk and we want this to solve the UV problems?
Yeah, exactly. I mean, at the end of the day, gravity is not UV complete. So you want some UV completion in which you can embed the QES formula. So you know that it's really a quantum gravity formula. I think that's
So you think that can be separated from the sort of non-perturbative? So this would still be perturbative, but it'd be like perturbative string theory.
Right.
And it would be well-defined. And it would give like some approximation to the boundary answer.
Yeah.
That would be better than if you just do gravity as a low energy effective field theory.
Yes.
Like, can you make that precise? Like, what is it that you would do more correctly if you did the string theory bulk?
Well, at least you would have some hope that you can embed it in a UV complete theory. We expect that string theory is UV complete, even though we don't know its non-perturbative definition. But the level of amplitude, it seems to be UV complete. And so you would hope that at least then you have some hope of embedding it in some non-perturbatively UV complete thing, even though you can't show at the level of perturbative string theory that it is non-perturbatively UV complete.
But is there some like sign that some matching to some boundary calculation that would say, okay, you got it correct, like to all orders in perturbation theory?
So I think there is actually a CFT calculation you can do of the entanglement entropy in this regime. I can tell you about it more offline. But the CFT calculation amounted to computing some stress tensor correlators. And people in recent years have developed a lot of technology to computing 1/λ corrections to that formula, to 4-point functions of stress tensors, say in n equals 4 super Yang mills. And I think you could take what they've done and use it to actually compute an entanglement entropy. That would give you some prediction for the bulk. Now in the bulk, I have no idea what you would do to match that. I don't know what the QES, stringy QES formula is, but at least I think I know how to derive a prediction from the CFT.
I see.
Yeah.
One question from your example. As far as I understood, you were comparing, you were subtracting, right? You have like your vacuum subtracted, and the excited state that you were choosing was that of a single graviton in a particular thing. But in your CFT computations, well, probably the answer is yes, since you did the computations and both match. But in the CFT formalism that you use that your states at a certain point you expanded around the vacuum. But it is surprising to me that the computations match, because a single particle state is not very similar to a no particle state. But perhaps we can discuss this offline a little bit more. But
yeah, the reason why it's small is because you're taking the small region limit, and in the small region limit, it actually is small. The correction to the entire
the region is small.
Yes.
It's
the small theta not limit that's making the corrections to the vacuum.
Thank you very much. Thank you very much.
Do you have more questions? No. Then we can thank Sean Colin again.